All right, now that we learned about absolute max and mean and how to find absolute max and mean of a function on a domain, now I want to look at some applications. Applications in real life, and in particular, we want to look at optimization problems. Optimization problems. So basically the goal here is to optimize. Optimize means maximize or minimize a quantity in real life problems. So one of the main goals of calculus and even applied mathematics, if you want to talk more generally, is to optimize a quantity. Well, which quantity, that depends on the context. So for example, in economics, you may want to maximize your profit or minimize the cost. Or in physics, for example, maybe you want to minimize the time that an object spends to reach, for example, a certain goal or certain target. Depends on the context. Or sometimes you want to maximize or minimize the distance, maybe minimize the distance that a plane, for example, has to go from one destination to another. Well, depends on the context. Sometimes maximize or minimize the quantity. Sometimes our preference is to maximize, sometimes minimize. And the quantity could be anything, depending on the context, could be the distance of something, time of something, cost of something, depending on the context. Okay, so in optimization problems, first assign letters to the quantities mentioned in the problem. Then find a connection between those quantities to write the quantity that you want to optimize in terms of one variable only. Say f of x. Then determine domain of f, the domain of f, and find the absolute max and mean of f of x on this domain using the methods we learned in the previous section. Okay, so in this course, because this is a calculus of one variable calculus, so our goal is to write the quantity we want to optimize in terms of one variable, f of x, because so far we have learned how to optimize or maximize or minimize a function of one variable. But this is because so far our knowledge is up to this limit. But in the next courses in Math 213, calculus of multivariable calculus, and in that course, you will learn how to maximize or minimize a function of two variables or three variables. So in that case and in that context, then you won't have to write the function as a function of one variable, because then you will know how to maximize or minimize even a function of two variables. So in that course, you just need to write the expression you want to maximize or minimize in terms of one or two or three variables. You don't have to reduce it to one variable, and then you can maximize or minimize. But in this course, because we only know how to maximize or minimize the function of one variable, we need to write our function in terms of one variable only. So what should we do if there are two variables? Let's say x and y. Well, if I can find a connection between x and y, let's say if I know that y is equal to, for example, 5x plus 1, then I can replace every y with 5x plus 1, and then I will have a function of one variable, even if originally I have a function of two variables. Okay, so this is the general idea about how you can do or solve optimization problems. But of course, we have to do lots of examples. I'll do some examples here, and I'll leave the rest as exercise for you. You have to lots of practice to get used to it and to be comfortable about how you can apply this method to solve optimization problems. So let's start with a simple example. So examples. Example, a garden is to be laid out in a rectangular area and protected by wire fence. What is the largest possible area of the garden? Of the garden if only 100 feet of wire is available for the fence. Okay, so see, we want to construct a garden by protecting it by a fence. So basically, we want to construct a rectangular fence, and inside will be our garden. Okay, so we know that the total amount of fence that we have is 100 feet. So we said, and we want to maximize the area. So we know the perimeter of the rectangle is fixed and is given. And we want to choose the length of sides of this rectangle so that the area enclosed area will become maximum. Okay, so we said that first we need to assign letters to quantities. Which quantities? Well, which quantities do we want to find? We want to find the length of the rectangle, right? So our goal is want to find the length and width of this rectangle, say X and Y respectively. So let's say this is X, this is Y, and we want to maximize. Want to find the length we want to find the length and width of the rectangle, say X and Y respectively. That maximize the area of this rectangle. Okay, so what is given to us? Given to us is the total perimeter is 100. That's fixed, that's given. So we can write total perimeter, which can be written in terms of X and Y as 2X plus 2Y, right? Total perimeter of the rectangle, 2X plus 2Y equals 100. And if you simplify this, divide both sides by 2, we get X plus Y equals 50. And what is the quantity that we want to maximize? We want to maximize the area of the rectangle, and the area of the rectangle, of course, we know is X times Y, length times width. Now, we said that because we have we only know methods how to maximize or minimize a function of one variable. So we have to write the quantity that we want to maximize or minimize in terms of one variable only. Right now, area is written in terms of two variables, X and Y. So next step is to write A in terms of only one variable. How can we do that? Well, we know that area is X times Y. So if I can find X in terms of Y or Y in terms of X and then substitute back, then I can write A in terms of one variable only. Well, right now we know the connection between X and Y. We know that X plus Y is equal to 50. So if I write down this and then let's say find Y in terms of X, doesn't matter, you can find X in terms of Y. But that right now, let's say I find Y in terms of X, then Y will be 50 minus X. And therefore, if I substitute back, I'll get area equals X times 50 minus X, which can be written as 50X minus X squared. Now that I found the formula for the function, the quantity that I want to maximize or minimize in terms of only one variable, then I need to determine the domain. Because remember, whenever you want to maximize or minimize, of course, you need to know the function, and you also need to know the domain. What is domain of this function, area function here? Domain means set of all inputs. What are the possible values for X? Well, what was X? X was the length of the rectangle. Well, the length of the rectangle for sure is non-negative, right? The length cannot be negative. So it's bigger than or equal to 0. And it will be at most 50. Why will it be at most 50? Because I know that x plus y equals 50, right? So the addition of x and y is 50 and each of them is non-negative. So each one will be at most 50, because if x or y is bigger than 50, then plus another number will be still bigger than 50, cannot be equal to 50. So if x plus y is equal to 50, each of them must be at most 50. So, well, that's what I wrote here, that because the x is the length of the rectangle is non-negative, x bigger than or equal to 0, and because x plus y is equal to 50, x and y, each of them must be less than or equal to 50. They can be at most 50, which means x must be less than or equal to 50. So if x is bigger than or equal to 0 and less than or equal to 50, that means domain must be closed interval 0 to 50. So we have the formula for our function, and we have the domain as 0 to 50. And the goal is to maximize, right? We want to maximize the area. So we want to maximize this function, area function, which is 50x minus x squared on this domain 0 to 50. But we already know how to maximize or minimize a function, continuous function on a closed finite interval. We provided a very specific recipe. So follow. Follow the algorithm. Provided last time to find the absolute max or mean of a continuous function on a closed finite interval. Do you remember? So first we need to write the candidates, which will be endpoints. Endpoints here are x equals 0 and x equals 50. So if I find the corresponding outputs, area at 0, remember the formula for area, 50x minus x squared. At 0 will be 50 times 0 minus 0, that will be 0. At 50, area at 50 will be 50 times 50 minus 50 squared. That will be also 0. And then we have to also look at the critical points. Critical points, that means I have to differentiate my function a of x. And then that will be 50 minus 2x equals 0. That gives me x equals 25. And then I can look at the basically compare the outputs, right? After I find the endpoints and critical points, then I need to compare the outputs, all the outputs, whether outputs corresponding to endpoints or outputs corresponding to critical points. Now the output corresponding to endpoints I already found, output corresponding to critical points. That will be, I have only one critical point, so the corresponding output with the corresponding output area at 25. So that will be 50 times 25 minus 25 squared. So that will be 25 times 50 minus 25, and that's 25 squared. So now compare A of 0, A of 50, which are the area at the endpoints, and area at the critical point, which is A at 25, A at 0 besides 0, A at 50 besides 0, A at 25 will be 25 squared. Which one is the largest one? Well, obviously, 25 squared is the largest one, and that will give me absolute max. So absolute max is the corresponding X value. So the output is 25 squared for which X value? For X value of 25. So absolute max will be X equals 25. Well, that's it. So the area becomes maximum if the length and width of the rectangle are X is 25. And what about the width, which is Y? Well, what was the connection between X and Y, if you remember? The connection between X and Y was 50 minus X. So Y should be 50 minus X, so it was 50 minus 25, which will also 25. So area becomes maximum if X is 25 and Y is also 25. Area of the rectangle becomes maximum if X and Y are both 25. But what type of rectangle is it then? A rectangle whose X and Y values are the same is a square. In other words, this rectangle with a fixed perimeter will have the maximum area if this rectangle is a square. Check that this fact is true in general. We proved it for this case, this example, where the perimeter was fixed and was equal to 100. And we showed that this rectangle must be a square in order to maximize the area. But it's always true. There was nothing special about 100. If the perimeter is fixed and, for example, is 200 or 250, doesn't matter. As long as the perimeter is fixed, perimeter of this rectangle, the rectangle will have the maximum area if the length and width of that rectangle are equal, meaning that if that rectangle is a square. Okay. Now let's look at the next example. Okay, example, the following figure shows an offshore oil well located at a point W. A point W that is 5 kilometers from the closest point A on a straight shoreline. Point A on a straight shoreline. Oil is to be piped from W to a shore point B and that is 8 kilometers from A. By piping it on a straight line underwater, from W to some point P, to some shore point P, point P between A and B, and then to B via pipe along the shoreline. Along the shoreline. If the cost of laying pipe is 1 million per kilometer, underwater and 500,000 per kilometer over land. Where should the point P be located to minimize the cost of laying the pipe? Okay, let me draw the picture and explain the situation for you. See, we have oil here at point W, and we want to pipe it. So there's point A here, and we want to pipe it to this point. So this is the point B, which is our destination. And there is water here. And here is the shoreline. Okay. Draw the water better. All right, so then we are going to, in order to bring oil from W to B, we will do it in 2 steps. First, from W underwater to some point P. So from W to some point P underwater. And the cost of this is 1 million per kilometer. And then from P to B over land, and the cost is 500,000 per kilometer. We want to find the location of point P that minimize the cost. Well, of course, like I said, in real life problems, sometimes we want to maximize the quantity, sometimes minimize the quantity. Of course, when in the context of cost, when we talk about cost, of course, our goal is to minimize it. Minimize the total cost. So the cost here consists of 2 parts. When you bring oil from W to P, some point P, well, that will be underwater, and that will be 1 million per kilometer. And then from P to B, that is over land, and that's 500,000 per kilometer. So where should we choose P? So that overall, when we add the cost of first part plus the second part, overall, the cost becomes minimum. Okay, so this point P, the choice of P is with us. Okay, so we could choose point P here. So in this case, let's say, for example, if this is, okay, so this will be 5, this was 5, right? This was 5, and this is 8 kilometers. So let's say, for example, if this length is 6, then you can find this length, right? Because using Pythagoras, if this is 6, you can find the length of this AP. And once you have AP, PB will be 8 minus AP. So if, let's say, W to P is 6 million, because this is 1 millimeter per kilometer, 1 million per kilometer, $1 million per kilometer. So then W to P will cost 6 million. And how much will be PB if you want to do a calculation? Let's say if this is, if WP is 6, AW is 5, so AP will be root 36 minus 25, which will be root 11. And therefore PB will be 8 minus root 11. So this one, 8 minus root 11, it will be some number times 0.5, because each kilometer will cost 0.5 million. So 8 minus root 11, the whole thing times $0.5 million plus $6 million will be total cost if WP is 6. Now, if WP is, for example, 7, again, you can calculate. So WP will be $7 million. In that case, PB will be smaller than this number here, right? So $7 million plus some number smaller than this times $0.5 million. You can see whether you can get a bigger number or smaller compared to the previous one. So of course, we have many choices for P, infinitely many choices for P. Because P could be basically any real number between 0 to 8 here. So if I call this distance, if I consider, how can I locate P? By determining the distance of P to A, right? So this distance A to P could be basically anything between 0 to 8. In one extreme case, if P is exactly on A, the distance between A and P will be 0. So that's, of course, again, one choice for me that, of course, I'm allowed to choose P on the point A. In that case, that means, I have to do a pipe underwater with 5 kilometers from W to P, and then 8 kilometers on the land, A to B. That's one extreme case. In another extreme case, P could be B itself. In that case, I can just do all of it under the water from W to B directly. That will be one extreme case. And of course, it doesn't have to be extreme. Like I said, it's possible that WP is 6 and then PB will be 8 minus root 11, or WP could be 7, right? So I have infinitely many choices depending on the distance that I choose for P to A. This distance could be 0, could be 0.1, could be 1, could be 2, could be anything, could be at most 8. Depending on how I choose my point B, how much distance I choose between P and A, then I will have a different cost. So I have infinitely many choices for the point P, and of course, each of those choices will lead to a certain cost. I want to know among all the choices that I can choose for P, which one will lead to the smallest cost, overall cost for constructing this pipe. So first we said that we have to assign letters. I want to find the location of P, right? So first, assign letters to the point P. Let's say I call it X and 0. Let's say if I choose here as my origin, choose as origin, and then A to P, I can call it X. Okay. And then this is the I can write origin here. Okay. Then P is X and 0. And we want to find X. So the goal is X such that the total cost is as small as possible. Now our next job is to write the quantity that we want to maximize or minimize, and in that case is cost, in terms of one variable only. It seems that the screen is freeze. Let me. Okay, it's good now. We want to find X such that the total cost is as small as possible. So our next job is to write the quantity that we want to minimize, which is cost here in terms of one variable only. Which variable? X, of course. So now we must write cost in terms of in terms of X. So let's see how we can write the total cost in terms of X. We must write the total cost in terms of X. So what is the total cost? The total cost is the cost of constructing pipe from W to P and then from P to B. So total cost, say C of X will be equal to the cost of WP plus cost of PB. All right, what is the cost of WP? First, I need to find the length of WP and then multiply it with $1 million. If I know the length of WP in kilometers, then I multiply 1 million, and then I will find the total cost in dollars. So PA, I'm assuming is X, AW is 5, so I just need to use Pythagoras. And then WP will be root 25 plus X squared. So this is equal to root 25 plus X squared. So this is length of WP. And then times 1 million. Plus, so this is cost of WP, the length of WP times 1 million. What about cost of PB? Again, I need to find the length of PB. That's very easy to find because length of PA is X, the whole length is 8. So length of PB is 8 minus X. Length of PB, and then times 500,000. PB, because it's over land, the cost is $500,000 per kilometer. So if PV is 8 minus X kilometers in total, then the cost will be that length times $0.5 million, which means that's that length times $500,000. So this is the total cost in dollars. So I can say that C of X equals root 25 plus X squared times 1 million plus 8 minus X times 500,000. And there you are. Then I also need to determine the domain. What is the domain? With domain, remember when you want to solve an optimization problem, you need to find the function in terms of one variable only and find the domain as well. Determine the domain. Domain is set of all inputs. X, here the input is X. X comes from which set? Well, X, if you look at the picture, is the distance between P to A. In the most extreme case, if P is A itself, X will be 0. X is distance of something, cannot be less than 0 for sure. It's at least 0, and it can be 0 potentially, because if P is A itself, X will be 0. So I can say that X is bigger than equal to 0, because distance is always bigger than equal to 0. And X is less than equal to 8. Because in the extreme case, if P is on B itself, then the distance between B to A is 8. In that case, distance between P to A, which is X, will be 8. But P cannot pass B, right? Because your goal is to bring oil from W to B. So in the most extreme case, P could be B itself, can't exceed B, can't pass B. So in the most extreme case, and P will be, X will be 8. And here I can say because distance between P and B is 8. So the domain here is 0 to 8. The set of all possible values for x is the closed interval 0 to 8, because x is bigger than or equal to 0 and less than or equal to 8, which means that the domain is closed interval 0 to 8. So I have the function, I have the formula for the function, I know its domain, I just need to find its absolute minimum. So now follow the algorithm provided last time. To find the absolute mean of C of x on 0 to 8. See, I have a continuous function. This function is continuous. This function is continuous. The addition is continuous. Continuous function defined on a closed finite interval. And we know how to find the absolute max and mean. Just fine. The candidates would be endpoints and critical points, and then compare the outputs. So candidates, endpoints, x equals 0 and x equals 8. So if x is equal to 0, then the output f of 0 will be first one, if x is 0, will be 5 times 1 million. That will be 5 million. Plus 8 times 500 is 4 million. That will be 9 million. Right? It's 8 minus x times 500,000. If x is 0, 8 times 500,000, it's 4 million. Plus 5 million is 9 million. If x is 8, f of 8 will be 25 plus 64, root 25 plus 64. It will be root 89 times 1 million. And the second term will be 0, right? 8 minus 8 is 0. This term will be 0. And we will have just this term, which is root 89 times 1 million. Now we also need to find the critical points. And C prime of x equals 0, the derivative equals 0. So that gives me derivative of this one is root u. Root u derivative is 1/2 u prime times u to power minus 1/2. So 1/2 u prime will be 2x. U to power minus 1/2 will be root 1 over root 25 minus x squared times 1 million. And then derivative of 8 minus x is minus 1. So minus 500,000 equals 0. So if I divide by 500,000, I'll get 2 over 1/2 times 2x is x. So 2x divided by root 25 minus x squared equals 1. See, I took this term to the other side, then I divided both sides by 500,000. That became 1. 1 million over 500,000 is 2. And then 2 times this will be 2x divided by this number equals 1. So that gives me 2x equals root 25 minus x squared raised to power 2. 4x squared equals 25 minus x squared. So this is 25 plus x squared. Let's see, the original function was root 25 plus x squared. So u to the power 1/2 derivative, we said 1/2 u prime, u to the power minus 1. So 1 over u to the power minus 1/2 u prime, u to the power minus 1/2. So that will be 1 over root u, which will be 1 over root 25 plus x squared. This one also root 25 plus x squared, 25 plus x squared raised to power 2 gives us 4x squared equals 25 plus x squared. And that gives 3x squared equals 25. X squared equals 25 over 3. And because x is positive, remember, in general, if x squared is 25 over 3, then the solution will be plus minus root of 25 over 3. But x is here is a distance of something, so it's not negative. And therefore, x will be root of this number, which is 5 over root 3. Now we have to check whether this number is in our domain or no. Because if it's not in the domain, then we have to just reject it. We are only interested in points which are in the domain. Now the domain here was 0 to 8. And this number 5 over root 3 is in domain. Side 0 to 8. Inside domain. This is, so we have one critical point here. So the corresponding output remember, we want to find absolute mean. To find absolute mean, we have to find the endpoints and critical points and compare the corresponding outputs to decide which one is the largest, which one is the smallest, which will give us absolute max and mean. Corresponding output will be f of, or c of in this case, we denote it with c. C of 5 over root 3. What is c of x? Root 25 plus x squared times this, plus 8 minus times this. So root root 25 plus 25 over 3 times 1 million plus 8 minus 5 over root 3 times 500,000. So this will be almost 800 33 sorry, 8,330,127. Okay, so lastly, compare the outputs. Which outputs? The outputs given by outputs corresponding to endpoints and outputs corresponding to critical points. So which will be C of 0, C of 8, and C of 5 over root 3. C of 0 was 9 million. C of 8 was root 89, if you remember. C of 8 was root 89 times 1 million. That will be almost 9 million. And 433,981. And C of 5 over root 3, which we saw that it's almost 8,330,127. So we have these three numbers. Remember, we want to minimize the cost, absolute minimum of the cost. So we have to compare the outputs, choose the smallest one. among these three numbers. Obviously, the smallest one is this, and that will give us the absolute minimum. So this is the smallest, and that means the absolute mean will be x equals 5/√3. So what does that mean? So that means if we choose the point P to be 5/√3 kilometer apart from A, or away from A, then we can say that then the total cost of constructing pipes and bringing oil from W to B will be minimized. Okay, guys, so this distance here from P to A has to be, this distance has to be 5/√3 kilometer in order to minimize the cost. You can check, you can see that if you choose P, the distance from P to A, anything other than 5/√3, for example, you choose P distance from P to A as 1 or 2 or 3, anything other than 5/√3, you will see that the total cost will be bigger compared to the case where you choose the distance to be exactly 5/√3. Okay, guys, so this is how we can solve optimization problems. These examples we did today were a continuous function on closed finite interval. So next time I'll do some examples for you where we have functions defined on open intervals to see how we can solve optimization problems in those types of questions, which will be basically the methods that we learned before the break, where we saw that if we have a continuous function on an open interval, how can we handle it and how can we find the absolute max and mean of such function if they exist. Okay, guys, so thank you and see you next time.